Hi, can you hear me?
Yes, sir.
Okay. Okay, so first thing is that looks like Siddharth Tower's classroom may not be available for us every Sunday. So I think we'll have to shift our lectures to other classrooms. So do you know Sathe College that we also have a classroom over there? So we will probably have our lectures in that premises from next Sunday onwards. I will announce the details once it is confirmed. Okay. Okay, so I think we can get started. So actually, I was supposed to upload a video related to coaxial circles, but I couldn't get the time to do that. I'll do it sometime maybe this week. But meanwhile, just wanted to discuss a few other things related to Power for Point with you, and we can proceed from there. So can you see my screen?
Yes, sir.
Yes. Okay. So actually, just one interesting idea I wanted to discuss with you, which we have explored previously also in the last lecture, but just to continue with that. So let me just draw this diagram again. And we solved this problem last time. So just to refresh your memory. So we have a circle with the diameter given, and we take any 2 points on the circle. So for example, something like this. Okay. And then you may remember that basically what we get is that the circle formed by these 3 points, and let me label them somehow. So this is A, B, for this P. So as you may remember that the circle formed by triangle LBP that was orthogonal to this given circle. Do you remember this property? We basically found that the whole 9-point circle configuration is hidden in this diagram because basically AS being the diameter, so these are altitudes. So we had found that this basically these are altitudes, and so therefore this point is actually the orthocenter of the big triangle ASL, and so therefore the circle with diameter, if I call this point H, then LH as the diameter, that circle is orthogonal to this given circle, right? That is what we had found last time. Let me just label the point slightly differently. And we had also explored some more properties related to that back then. So just wanted to continue investigating this diagram a little bit, and let's see if we find anything more interesting about this diagram. So let me make one construction. So this point, the center of our circle, let me call that O. Okay. So let me consider a circle. So consider the circumcircle of triangle SOH. Okay. So there will be a circle passing through the point SOH, and let it meet again at some point P. Okay. So PHOS, they are cycling. Something like this. Okay, so this point P is over here. And then let me construct one more point. Also consider a point like this. Let me call this point D. So consider a point D on BS such that AD is parallel to the base. Oh, actually, both of these became S. Let me call this something else. Okay, temporary. Okay, so AD and SK are parallel. That is what is given. Okay, so these are two separate points as if you think about it. So the first one is this is constructed using this circle. And now it should be called KOH. So KOHP are concyclic. That is how we constructed point P, and point D is simply this parallel segment. Okay. So first thing maybe I would like us to figure out is, can we compute HD into HB in any way? So I'll give you some time to think about this question. HD into HB. Is there some way to compute that value? So in this first part, the point P is not important. So you can just focus on this second piece of information, ignoring point P for the moment. So in fact, I mean, you can draw a new diagram where the point P is not there in the picture, just to simplify things. So you can focus on just the line AD, which is parallel to the base. And can we find HD into HB? And in fact, to encourage that, let me just temporarily remove this point P from the diagram. So that your focus is the attention of the focus of your attention is point D and not point P.
Sir, can you please show the main question?
Main question, I mean, the one which we solved earlier?
Yes, sir.
Okay, just a minute. Okay, now if you can see the screen, then question 3 is the one I'm talking about. So in our diagram, the labels are slightly different, but it's the same configuration. So there is a circle with a diameter, and you take any 2 points on that circle, and we basically join them together. Or the reverse, you can start with a point outside the circle and you join it to the end points of the diameter. But basically, what we had found is that we get 2 orthogonal circles.
Yes.
So I hope you remember this question.
Yes, sir.
Okay. So I've started with the same diagram. So this point L, which is taken outside our diagram circle. So we join them as usual and we get the orthocenter configuration. And to that, I've just added this construction that consider line AD, which is parallel to the base ASK. Okay. And so we are interested in computing HD into HB. I am not telling you why right now, but just try to find HD into HB. We'll find something interesting about this question soon. So first, of course, SD into HB looks like some kind of power, right? So do we already know any power related properties about the orthocenter H? Yes, Om, you have found the answer?
Yes, sir. Sir, AH square.
AH square, yes, correct. And there could be at least two different approaches which I know to prove that. So can you just quickly indicate whether you use some
Uh,
like angles or any?
no, sir. Means first of KSAB is cyclic. So
Yes.
BH into BS is equal to.
Yeah. Okay. Got it. Got it. Yeah. Don't tell the whole answer, but yeah, I got the general direction.
Okay, okay. And then parallel line and similar
Yes,
triangles.
it's correct. But you can also try the problem again without using power. It can be done with angle chasing also, if you think about it. Now that you know the answer, right? So you know what property might be true. And so if you can prove that property,
Yes, sir.
but just to indicate how you can get started with the approach which Om has mentioned. So as I said, first try to find any power type expressions about point H that you already know. So basic power theorem, like when you have two chords intersecting, we can write this, right? So HB into HS is equal to HA into HK. So this everybody understands. But what we have to find is not HB into HS, we have to find HB into HT. So we have to replace this HS by HT. So what should I multiply or divide the expression by to achieve this transformation? So can I multiply and divide both sides of my equation with the ratio HD upon HS? Correct. If I do that, then my LHS will become what I want. Correct. And now what happens to the RHS?
Sir, we know that HD upon HS is equal to HA upon HK.
Yes, correct. So therefore the RHS will become. So RHS is HJ into HK into HT upon HS. And from the triangles which you just mentioned, can you see that this ratio is going to be again HA? Because as I said, because of the parallel lines. So this is the first thing we need to establish, that whenever you see parallel lines like this and we are talking about product ratios, always take your mind to similar triangles DPT. That should be the first step that comes to your mind. So if you apply that in triangle, which triangle DHA, which is similar to triangle SHK, then we can write the ratios. So DH upon SH is equal to HA upon HK, right? And if you rearrange this, do you see that this is also equal to HA? This part, this is also equal to HA. So therefore, the entire product that we get, so HD into HB will be equal to HA square. Okay, is everybody with me? So again, take the time to understand this is a very small problem, but even that has some important techniques that we need to keep in mind, that we wanted to find HD into HB. So we first found something which is close to that, try to get as close to it as possible. So that was HB into HS. And then from that, what do we need to modify to get to what we want? So just multiply or divide by the suitable factor. And luckily, the problem was so designed that that factor was nicely turning out to be HA. So that is how everything worked out. So HD into HB is equal to HA square. So what does that mean in this diagram? From the power of a point theory that you know, if HD into HB is equal to HA square, does that
Sir,
remind you
so
anything?
HA is tangent to circle of ADB.
Correct. So HA, if I consider the circumcircle of ADB, right? Let me just zoom in the diagram a little bit. So this circle, I'm just drawing it roughly. So this circle will have HA as a tangent. And so basically we are using again the converse of the power theorem. So power theorem says that when we have a tangent like this, then HA square is equal to HD into HB. But that statement also has the converse, that if HD into HB is equal to HA square, then that HA has to be the tangent to this green circle. Okay. So therefore, what I was suggesting is that if you can prove that tangency in some different way, even that can be used to show this power result, right?
Yes, sir. Yes, I got it.
You got it? So what should we use? Which theorem?
Sir, we join BA and then we can prove that ABD is equal to, so ABP is equal to PAH.
Yeah,
And
just
so,
let me just clean up my diagram a little bit. Oh. So as you said, let us join AB, and then what do you want to show?
so if we show that angle ABP is equal to PAH, then it will become tangent.
Correct. So we are using converse of tangent secant theorem. So this black angle which I marked over here, if I show that also equal to this angle, then we can apply converse of tangent secant theorem. And is that true?
Yes, sir.
Because of basic angle chasing, right? Because this black angle, so we have to use the fact that AP is parallel to the base. So this angle is equal to this angle, AKS. And then AKS and ABS, they are equal, right? So therefore angle PAH.
Because ABKS is cyclic.
Yes, correct. So PAH will be first equal to angle AKS, and which is equal to angle ABS. So therefore, this angle also becomes the same one. And so by converse of tangent secant theorem, you will get the same result. That that circle is tangent. The circle of APB is tangent to HA. And therefore, then applying the forward result of power theorem, you get HA square equal to HP into HB. This was point D. Accidentally called it D. Okay. So this was the result of this point D. Okay. So just give 1 minute to copy anything that you want or write anything. And then we'll go to the second part. So where we are considering the circle KOH. So we'll come to that. Okay. So I'm going to draw a fresh diagram now. Instead of adding that point P to the same diagram. So you can see this is like part 1 and part 2. So part 1 was we found this property about the point D. Now I'm going to show part 2. And in part 2, again, the basic diagram is the same. So again, we have a circle. So again, we have a circle. A and B. And same as before, if we join the not a very good diagram because this is supposed to look like a perpendicular. But anyway. So now I'm going to consider circle KOH. So consider circle KOH. And in fact, let it meet the main circle. So circle ABKS at a point P. Okay, so I'm considering this circle passing through KOH. So I won't draw the full circle, but just this part. And so this is what I'm calling point P. So now in this part, what you're supposed to find is show that HA is equal to HP. So in other words, triangle HAP is a cyclic isosceles triangle. So now in this part of that point D, which I had shown earlier, is not there in the picture. So we are only focusing on point P. I'm calling this as question 2. Yes, Om, you have solved it.
Sir, I done by angle chasing.
Okay, yes. So we'll give some time for others to think also. But yes, angle chasing is the right approach, or at least one of the easiest approach to follow. Yes, Ruhan, you also solved it. Okay. So for others who are still thinking, just trying to think aloud that when you encounter a problem like this, what are the thoughts that should come to your mind? That where am I right now and where do I need to go? So first is this show that is given in terms of length, but I can easily convert that into equivalent angle statement, right? And probably, the angle approach might be easier to tackle because I am given a lot of cyclic quadrilaterals, 90-degree angles. So I have a lot of information about angles. And so naturally, my problem also, if it is posed as an angle problem, maybe it might be easier to make progress. So the first thing we understand, this is equivalent to prove that the triangle HAP is isosceles, which is angle HAP is equal to angle HPA. This is what I want to prove, right? And let me just draw the lines which I'm interested in. So this triangle I want to show isosceles. And so if I have to try to chase the angles, the two angles which I want to show as equal, right? So how do I get started? So for example, look at this angle PAH. Okay. Is there any way that by which I can manipulate this angle and show that this angle is equal to some other angle and so on and so forth? And what are the other angles in the diagram which I can relate this angle to? So for example, I'll just write the statement angle PAH is equal to. And now, try to fill in the blank that how can you chase this angle further to get some information. So those who have solved it, did you do something similar?
Yes, sir.
I showed angle, those two angles, angle HAP and PAH, HAP and HPA as difference of two congruent angles.
Difference of two congruent angles. Okay, interesting. Yeah, that will also be fine. So Rohan, can you give me a hint which angles you are talking about?
The angle OPH
Okay.
and OPH equal to OAH and OPA and OAP.
I see. Okay. Oh, yes. Yeah, very nice. Okay, so I think we have at least two different approaches available here. Maybe one more if anybody has another idea. But so for example, let us start with angle PAH. So angle PAH is equal to clearly angle PAK, correct? And so PAK, whenever you have angle in the circle like this, we can always relate it to any other angle inscribed in the same arc. So therefore, that will also be equal to angle P. Oh, no, not this angle. Sorry. PAK will be equal to PSK. Okay. So it's not necessary to draw the angle, but just for illustration, I'm doing that in case anybody is wondering. So angle PSK. But from there, we have not still used the green circle which is given, right? KOHP cyclic is not used here. And so to use that, what can we do with angle PSK? We need to somehow bring it to the green circle. And so if you know that central angle, and so we have to exploit the fact that this point O is also the center of the big circle, right? So therefore, can I write PSK is actually half of angle POK, right? And so what that does is that angle PSK is now taken to the green circle, POK. And Once I'm on the green circle, again, I can try to chase some angles. So how much is POK going to be equal to?
PHK.
PHK, correct? So I'm sort of completing the loop here. If you see that I started with something related to triangle PAH, and finally, so PHK is just the exterior angle. If you see, PHK is the exterior angle of PHA. And so, I mean, at this point, you can see multiple ways to proceed. So, for example, we know that PHK is actually the sum of the two angles we want to show equal, right? So, PHK is equal to HAP plus HPA. And so, therefore, combining this and this, it means that in fact these two angles are equal. Right. So, for example, like here in this, I'm getting angle PHK is 2 times angle PAH. But PHK is also equal to just this, what I wrote. And so therefore, what it implies is angle PAH is equal to angle HPA. Okay. So this was, so Om, was this the approach which you?
Yes, sir. Yes, same approach.
Okay. So here you see again, we continue to transform the given to prove that. So the original to prove that, we change it to that, prove that these triangles are equal. But do you see this is one more characterization of isosceles triangle, that one exterior angle is equal to twice the opposite interior angle. So angle PHK, this is twice the interior angle. That is also equivalent way of proving that something is isosceles. And that is what we used here. So, I mean, keep all these equivalent statements in mind, because in different contexts, a different one of them will be useful. So always, keep your eyes open for any such possibilities. Okay. So then coming to the approach which Rohan mentioned. So let me try to construct the way I understand it. So what he said is that let us show the two angles HAP and HPA as the difference of two angles which are known to be congruent. And so, for example, we can write angle HPA as angle OPA minus angle OPH, and angle HAP will be equal to angle OAP minus angle OAH, right? And so if I can show that these corresponding pairs are equal, then also I'll be done, correct? And so out of that, do you see that the first pair OAP and OAP are going to be obviously equal, because O is the center of our circle. So OPA is a cyclic isosceles triangle. So this is clearly true. But what about the other pair? How can you show that OPH and OAH are equal? So again, we have to exploit the given cyclic coordinate, whatever we have, all the concyclic points. So if we start with angle OPH, right? So angle OPH, can we chase that angle and show it to be equal to which angle can I say? OPH is equal to?
OKH.
OKH, correct? So O, because PH, OK are cyclic. So this is OKH. And now do you see why OKH and OAH are going to be equal?
Yes.
Because again, it's a triangle AOK, which is isosceles. So therefore, this is nothing but angle OKA, which is equal to angle OAK, which is equal to this. So again, very simple, elegant solution, simple angle chasing. Okay. So everybody needs to appreciate these various possibilities, that how you can attack the problem. And so what we have shown is that HA is equal to HP. So this was the second part. And what was the first part? What did we show in the first part? That point D, right? So if we combine the first and second part together, what can we say? So let me just draw the point D in this same diagram. So point D we had constructed by just taking the parallel line like this. So putting part 1 and part 2 together, what can we say? So part 1 allowed us to conclude that HT into HP is equal to HA square. And from part 2, we got that HA is equal to HP. So therefore,
So HP is tangent to circumcircle of PDB also.
yes, correct. Correct. So therefore, I mean, just putting this together with what it means that HT into HP is also equal to HP square. And again, using the converse of the power statement. So therefore, HP is tangent to the circumcircle of BDP. Okay, does everybody follow this? Okay, and now there is going to be part 3 also. And you may be wondering, why am I doing all of this? Why did I suddenly get the urge to do all of these things? I'll tell you. It's a very interesting surprise at the end. Okay, so now part 3 is show that angle BPD, okay, is equal to angle, which angle ASB. So now I'm using point P and point D both together. In part 1, only point D was there. In part 2, only point P was there. But now P and D are both going to be important. Oh, I'm sorry. Actually, this is not the right statement. The right statement is 90 minus this angle.
Sir, is it that MPH are collinear?
I don't know. I don't think so actually. Because we know MH is going to be perpendicular to the base, right? Because that is just the third altitude. So I don't see any obvious reason why P has to lie on that line always. I mean, if you're finding that in a rough diagram, just try drawing a slightly different diagram, maybe. Yeah, unless you're able to prove it, then we have to consider it. But at least intuitively, I don't see a reason.
Sir, I have drawn two diagrams and it is coming
Mhm. I have to think, but I'm really doubtful actually. MPHR collinear is what you're claiming. No, at least from what I can see, I mean, it may look that way in particular diagram, but I don't see a reason why it has to be true. In fact, I can see why it will not be true always. Okay. So just adding a few lines in the diagram to help us do the next steps. Okay. And again, I'll just start thinking aloud that what can be the starting point of this analysis. And so I just repeated at the top the information that is given, which I have to use. So I need to use these two cyclic quadrilaterals. PHOK is given. And now that we have found, so we have to use the part 1 and part 2 also. So now that we know HP is tangent to triangle BDP, circle BDP, right? So that creates some additional pairs of equal angles. So which angles? I mean, basically this property, the HD into HP equal to HP square, or the tangency. Can you think of any triangles, similar triangles, which are related to these properties? So this is actually a set configuration which you also always keep in mind that whenever you have these properties, right, HD into HB equal to HP square. So let me just draw that separately so that this gets sort of imprinted in your mind that whenever I have any such tangency, right? So by tangent secant theorem, can I say that these angles are equal, right? And obviously this angle is common. So in fact, what I get is triangle HDP is similar to triangle HPB. So these 3-4 things are all equivalent. Saying that HDP and these are similar is the same as saying that HP square is equal to HD into HP. And it is also the same as saying that segment HP is a tangent to this circle which we have drawn. So just keep this in your mind all the time that all these are equivalent. And so if you have one of these occurring, immediately we can use the other properties. Okay, this is a very standard pattern that comes all the time. Okay, so do you see that this is happening in our diagram also? That we have So in our case, we know these two properties. We know that this HP square is equal to HD into HP is given, or rather we have proved it already just now. So therefore, which triangles are similar and which angles can be marked as equal?
So angle PBH is equal to DPH.
PBH, no, not PBH. Yes, PBH, correct. PBH and DPH, correct. These angles are equal, correct? And you see, these angles are useful for us because we are interested in BPD. This is what we want to find. So now you see, can I express BPD as the difference of two angles? Okay, so if I use that as a starting point, that let us express angle BPD as what should be equal to BPH minus angle DPH. Okay. So what can be the next step? So if you look at this, BPH is a kind of a complicated angle because it involves this point P and H, which are on the green circle, but point B is not on the green circle. So we have half information, like half of the points of interest are on one circle, the black circle, and half of the points are on the green circle. And so when you have a situation like this, it's always useful to split one big object into two smaller objects, which are easier to manipulate. So can you think how we can split angle BPH into two smaller parts, which can be independently manipulated?
Sir, which angle?
BPH. Can we try to split BPH? So this first term, right? I want to say that this is equal to something else. Yes, Kana?
No, I had a different solution.
Okay, yeah, okay, go ahead.
So BPD, so we have to prove that BPD is equal to 90 minus ASB.
Yes.
So that ASB is equal to AKB.
Okay.
And minus AKB is equal to BHK. And BHK is equal to BMA.
No, wait. AKB is equal to B.
90 minus AKB is equal to BHK.
Yes, correct.
So we have to prove that BPD is equal to BHK, but we know that BHK is equal to BMA, which is equal to 180 minus AHB, which is equal to BHK.
Okay, yeah, just a minute. So what I understood so far is that we want to show that BPD is equal to this angle, BHK. And so from there, what you said, BHK is equal to?
BHK is equal to BMA.
BHK is equal to BMA. Yes, that is correct.
So we have to prove that BPD is equal to BMA.
Correct. So what do we do after that?
I haven't been able to find a proof that BPD is equal to BMA yet.
Okay. Yeah, but yeah, maybe this can be useful. So we have shown that this angle, which was kind of far away, right? We have brought it closer to our desired angle. So BPD and BMA look much closer to each other, but we still have to complete the proof somehow. Okay, so I'll just keep this thread in the back of my mind that if we can complete this proof, this thread what you are indicating, you may get one more solution. But coming back to the proof which I am suggesting, so what I'm saying is that angle BPH, right? Can I split this angle BPH into two smaller parts which are easier to manipulate? So for example, how about this angle BPO plus angle OPH? Is that fine? BPO plus OPH. And the other angle DPH will remain as it is. So in fact, that other angle DPH also we can manipulate, but we'll come to that later. So we'll first finish the calculation of this first angle. So angle BPO plus OPH. Okay. So what can we do next? And in fact, let me do that also. So angle DPH, right? So because of what we showed earlier, DPH is also equal to angle PBD or PBH. So this red angle which I marked, right? So these angles which are equal, we are using that. And you'll see that that same angle will also be angle PKS, right? So we have this chain of properties, angle DPH is equal to angle PBH, which is angle PBS is equal to angle PKS. Okay, so I can replace this term by minus angle PKS. And what about the remaining two terms? So can we see some way of manipulating these two terms? And remember where we want to go. Finally, we are interested in reaching 90 minus ASB. So any angles, ASB is, an angle inscribed in our big circle, the black circle. So that is the direction we want to go.
Yes, sir. So angle OPH is equal to angle OKH.
Correct. So this is equal to OKH.
And angle BPO. So we can use that O is a center.
Yes, correct.
And
so I mean, I'll just draw the fact that BOP is isosceles, right? So if I just consider this the altitude, right? So I have a 90-degree angle over here. And so BPO can be written as 90 minus that middle angle, right? So here again, actually, there is one configuration which can be, so just let me draw that part separately, because this again, so you see, these are small things which occur all the time. So this is like theme one, the idea of tangent to a circle, and tangent plus chord, tangent plus secant. That is one thing. This is one more thing that will occur all the time, which is suppose we have a circle and we have points O is the center, B, P. Okay. So when this configuration is there and we are interested in angle BPO, then do you see that angle BPO, which is also equal to angle BOP, right? Sorry, PBO. Okay. And so in fact, they are both going to be equal to, if I just draw this 90-degree angle. So it is going to be 90 minus this angle. TOP, correct? And in fact, if I have any other point on this circle, so let me take any other point. Okay. X, let's say. Then do you see that? And in fact, this is equal to 90 minus angle BXP. Because TOP and BXP are going to be equal. And why is BXP and TOP equal? Because as angle BOP, which is the central angle, which is going to be 2 times angle BXP. So therefore, angle TOP, which is half of that central angle, will be equal to BXP. Okay, so putting all these things together, do you see that I can say angle BPO, which will be 90 minus any angle inscribed in the same arc. So BXP, for example. Okay, so I can call this theme 2. And what name can we give to this theme? Maybe isosceles triangle in a circle. Something like that. I don't know. Maybe you can come up with a better name. Okay, so if this part is clear, can we apply that in our question?
Yes, sir.
And what can we say? So angle BPO So how much is angle BPO going to be? 90 minus any angle inscribed in on arc PB, right? So for example,
Angle BKP.
correct. So angle PKB or BKB. So you see how term by every term we have manipulated to something else. So BPO, this term has become 90 minus BKP. OPH and OKH are equal because obviously they are marked inscribed in the same arc. And then PBH is equal to PKS. Okay, so we are very close to finishing the problem now. So firstly, we have to show that BPD is 90 minus something. So that 90 degree we wanted in our expression. So that 90 degree has come in our term now. And so now just the remaining terms, if we can adjust. So what are the remaining terms? BKP, OKH, and PKS. But do you see now? And OKH also, see OKH is actually the same as which angle? SKA, right? Minus angle PKS, or instead of that, let me write SKP. So you'll see that in fact all these three angles are at vertex K only. So can we combine them and what will we get? And so let me take the minus sign common, because we are interested in 90 minus something. So can we write this as 90 minus which angles? BKP minus SKA plus SKP. So if you see BKP plus SKP, so BKP is, if I just draw the segment BP, KP. Okay, so the first term BKP is this angle. The last term SKP is this angle. So the first term plus last term combined is this whole angle BKS. And out of that we are subtracting SKA. So this is the part which we are subtracting. So what will be left with?
AKB.
AKB. And so do you see that will be equal to ASB?
Yes.
So therefore this is equal to 90 minus AKB, which is equal to 90 minus ASB. Okay. So there are a lot of steps involved in this. I certainly won't say it is easy to see all these things, but see, with small steps, one step at a time, we did this. But we never had to use anything, difficult, which is never taught in school or they never learned before. Simple angle manipulation, but doing it very systematically, one step at a time. That is how we did this. Okay. So anyway, as you know, the lectures get recorded and put on YouTube. So any step which you are stuck or not able to understand, just go back, rewatch this part and make sure you understood every step thoroughly. And not just what is the step, but how we came up with the motivation, that why we thought of doing this, why we thought of doing that. That is also important. Okay, so this is the third result. So So again, revising the three parts that we showed. So the first part that we showed was that HD into HB is equal to HA square. Then the second part we showed that HA and HB are equal. So this isosceles triangle. And the third part was this angle BPD we computed. Okay, so now it's time for me to tell you why we did all these things. So do you know what we just solved?
Sir, is that BP is parallel to K?
BP is parallel to K. What is it? I don't know.
So like an angle we concluded and no sir, no, sorry sir.
No, yeah, at least in my diagram it doesn't look that way, so I don't think so. But do you know what we just solved? So in fact, we have solved question 2 of this year's International Mathematics Olympiad. So this was problem 2 of IMO 2023, which just concluded 10 days ago, as you know. And our team has done quite well. We are 8th in world rank. And we had been ranked 7, but that was more than 20 years ago, if I'm not mistaken. So this is definitely a record for our team in the recent memory. And so what we just solved was question 2 of that very difficult paper. And so what I want to indicate is, what is the takeaway from this? And by the way, the way I expressed this problem, it is if you go and read the question 2 of IMO, you will not see immediately why this is the same problem. But trust me that, so this is your homework. Prove that we have solved question 2. So we have to so this was step 3, but after that still there is a step 4, which I have not mentioned over here. But if you fill that missing gap, question step 4, then we will realize that actually this, what we have done really is question 2 of this year's IMO. Okay. So this is your homework to figure out how all of these things put together will result in that particular problem. And in fact, so that is why, the notation, the points, the names of the points I've chosen are very carefully chosen in that way. So that if you take this diagram and compare it with the IMO question, you'll see that it nicely matches that one. And very, very funny thing is that in that IMO question, they are talking about triangle ABC. But in our diagram, there is no point C at all. And still I'm saying that it is the same question. So, it's very funny that that point C is given in the original question, but it is completely optional. But okay, if you really want to know where the point C should be in this diagram, you just take this perpendicular and wherever this point. So this is supposed to be point C in that IMO question, but we never required this point C. So it's a very paradoxical thing that it's a problem about a triangle, but one of the vertices of the triangle is not required at all to solve that problem. So even something like that can happen. Okay. So what are the takeaways from this, if you ask me, that what you need to learn? Maybe the first takeaway is that, yeah, certainly IMO can be very hard, coming up with these steps, like think about step 1, think about step 2, think about step 3. This is not trivial. Okay. It takes a good amount of maturity, experience to think of these intermediate steps. But on the other hand, we can also say that, IMO is not that hard also. I mean, it is not that you need to read some, 10, 20 theory books, some complicated theorems, which you never studied before, and then you can solve the problem. Each step that we did in today's problem was based on something we already know. For the most part, I would say 90% of what we did today was simply angle chasing, right? Using cyclic quadrilaterals, using tangent secant theorem. All of these things are taught to us at school level. But how to use those basic ideas and still create a fairly challenging problem, at least for our level. So that is what Olympiad is all about. And of course, this was the hardest of the lot that we will deal with, because we are still doing RMO, pre-RMO, RMO, INMO. So we have many stages to go before we are going to deal with problems of this kind. But it's good to realize sometimes that that road is not that hard to travel. It's going to be one step at a time. So maybe the first few questions you are going to do, they will involve only one intermediate step. So this intermediate step, right? Step 1, step 2, these are the ones which we need to figure out, that how do you guess that this is the next step. So this is the step 1, this is the step 2. So which I always say, that if I take a hard problem like IMO problem and break it down stepwise, then every step looks very simple and at least manageable, I would say, if not simple. But how to break that big problem into these 4 smaller steps, that is sometimes the difficulty. Okay, and that you need to practice and figure out. So, I mean, if I gave you the IMO question to directly, there is a very small chance that you will get directly in one shot. But having broken it down into these steps, now there is at least some maybe 20% chance that we will solve this problem. And if I break down this problem even further into even smaller bite-sized pieces, then everybody will get it, I'm sure. Okay. So I mean that is part of my job as a trainer to help take what appears to be a difficult problem and break it down into smaller pieces. But that is what you also have to do whenever you encounter a difficult problem. See what are the small steps that you can take to solve that problem completely. Okay. So as I said, still there is one question, step 4, which is remaining, but that is your homework. So your homework is to connect this problem, whatever we did right now, with the actual problem to of IMO, which is now published online, so you can easily find it. And there are, if you Google, you will find so many solutions of that IMO problem, and every solution has something new to teach us. Okay. So with that out of the way, let us come back to our power point. And somewhere, at least in the initial stages, you see the power point was involved in this proof, at least. So you see how in that IMO problem, there was nowhere mentioned that power point is going to be required, but the statement of that problem was that prove that some particular segment is tangent to a given circle. And so that exactly comes back to what I'm saying, that when you see, okay, I erase that diagram, but that those 3 statements which are written, right? So when I have to show that some segment is tangent to some circle, I can convert that into tangent secant theorem, the power of a point expression, and I can approach the problem that way. So that was the same idea which led to this solution for me at least. Okay. So with that done, so coaxial circles, I'm still planning to teach it through a recorded video. So instead of covering that here, I want to show one more property related to power of a point, which is very useful actually. So this is the idea of a pedal triangle. Okay. So I don't know if anybody has heard this term pedal triangle before. Not pedal. So pedal is like feet in English. The sort of the letters PED often refer to the foot of something, and so that is why this triangle is called the pedal triangle. And so what we do is in a triangle ABC, right? If I take any point inside the triangle, okay, and if I drop altitudes from this point to the 3 sides of a triangle, okay, then this triangle DEF is called the pedal triangle of P with respect to triangle ABC. Okay. So basically every point in the plane will have its own pedal triangle with respect to the given triangle. Okay. And as the point P moves, you can imagine how this pedal triangle may change its shape. And for some special points, this triangle DF is also special. So for example, can you tell me anything special about the pedal triangle of, so what is the pedal triangle of the circumcenter? Anything special about this pedal triangle?
So it's midpoint of sides.
Correct. So that the feet of the DEF will be the midpoints of the side. So what will that triangle DEF be like? Any problem?
9-point circle, right?
It's a 9-point circle. And I mean, you see that triangle will be similar to the original triangle.
Yes.
With half ratio, right? So the triangle formed at the midpoints of the sides is similar to the original triangle with half ratio. Then similarly, pedal triangle of orthocenter will also be on the 9-point circle, right? And in fact, you may also know that for that triangle, the ABC are the X centers, right? So ABC are the X centers of that pedal triangle, the pedal triangle of the orthocenter, and so on and so forth. So for some special positions of the point P, you get some very interesting properties. And by the way, this point P doesn't have to be inside the triangle also. It can go outside also. So point P can be anywhere outside the triangle ABC also. Does anybody know anything special about these feet of the altitudes? When I take any point in the plane and I draw altitudes on the three sides, this point DEF, does anybody know any properties?
Sir, like a P line on circle circum of ABC.
Yes. So there's
So
something
Simpson line.
Simpson's line. So I don't know if we have studied all of this Simpson's line. So Simpson's line is the line formed when the point P lies on the circumcircle of ABC, right? So if I choose the point P somewhere over here, okay, so point P is on the circumcircle of ABC. And from here, if I draw the altitudes to the three sides, so even in my rough diagram, you see that they appear to be collinear. So in this particular situation, when the point is on the circumcircle, this pedal triangle is no longer a triangle because the points are collinear. So in this case, we often call it as a degenerate triangle. So degenerate meaning that it's sort of demoted from the status of triangle to simply a line. So the pedal triangle becomes a degenerate triangle when the point is on the circumcircle. And by the way, that is a if and only statement. So if there is a point for which the feet of the altitudes are collinear, then you can show that that point has to lie on the circumcircle. Okay, that is what we call the Simpson line. So again, this is not that complicated, so I won't plan to cover this on my own. But if anybody doesn't know about this, please read up about Simpson's line, and there are many interesting properties related to that. But I am not interested in the Simpson's line particularly as such. What I am interested in is, let this point P be anywhere in the plane, doesn't matter. Okay. I want to answer the question, what is the area of the triangle? Area of this pedal triangle. Okay. I want to find a formula for this area. And so naturally, one thing we'll realize is that if that point P lies on the circumcircle, then that area has to be 0, right? Because the triangle does not exist at all. So we sort of know, we know two special cases, let us say. So case one that we know, let point P lie on the circumcircle of ABC. In that case, we know that the answer of the area is 0. Okay. And case 2, if the point is at the circumcenter, right? So the point is at the circumcenter. Of triangle ABC. In that case, what will the area be equal to?
1/4.
It will be 1/4 of our original triangle, right? It will be 1/4 of the area of ABC. By the way, this square bracket notation, I don't know if you have seen it before, it's fairly standard. So square bracket with a polygon in inside, which means the area of that polygon. Okay. So the area of triangle DEF will be 1/4 of ABC because the triangle is similar and of half ratio. So these two special positions we know. But what I'm interested is to find out this area for any position of the point P. And so let me give the formula first and then we'll see how to prove it, because looking at the formula may give you some inspiration that it will be surprising to know that that is the formula. So as it turns out, the area of this is equal to correctly. Oh, sorry, I think there's a term of 4 over here. Just confirm once. Yeah, 4 hours. So what is this P gamma? So gamma is my circumcircle actually. So let gamma be the circumcircle of ABC, which I'm not drawing this diagram. So basically P gamma is the power of point P with respect to that circumcircle. And so the power of that gamma with respect to the circumcircle times some constant. So that constant is the area of ABC. And I should also add a minus sign over here, because when the point is inside the triangle, I have to explain why that minus sign is for at some other point. But right now, just we understand that when the point is inside the circle, inside the triangle ABC, right? Then, or rather inside the circumcircle, then the power is negative. And so just to make the whole area positive, I'm adding this minus sign. But I will give more detailed explanation of that later on. But this is the expression of the area of the pedal triangle. And so first things first, do you see that this area definition is matching these two special cases? So when the point is on the circumcircle, what happens to the power?
Power becomes 0 and R
Yes.
is R.
Yeah, I mean, the power becomes 0. So the other terms don't matter, right? So power becomes 0. So this answer will be 0. So therefore, this is satisfied. And what about when the point is at the circumcenter? So the formula of the power we know is d square minus r square, right? The distance from the center minus r square.
So D becomes 0.
So in that case, d becomes 0. So therefore, power is simply minus r square. And so if you put minus r square, this will become minus minus plus. So it will be 1/4 ABC. Okay, so at least this formula seems to satisfy these two special cases. But what I'm interested to show is that for any position of point P, this is true. And so you see, it's actually very interesting that the area of the pedal triangle only depends on the distance from the circumcenter. So this OP distance, if it's constant, so in fact, I can think of a circle of some fixed radius, right, centered at O. And if this point P moves around this circle, you see the pedal triangle shape will change so much, but its area does not change. Because in that case, everything is constant, right? ABC is fixed, capital R, which is the main circumcircle of ABC, is fixed, and the power is also fixed. So all the pedal triangles of the points along this particular circle, they are all going to be equal. So that's a very interesting property. So, you know, the power of a point shows up in some very interesting ways. But of course, we have to prove this property now. And a question like this has so many rich approaches possible. There can be simple geometric approach, there can be some trigonometry, there can be some coordinate geometry, there can be some complex numbers. At least, you know, 5-6 different approaches might be possible for this question. And as and how you learn all of these theory, right? As you learn some more trigonometry, come back to this question and try it again with trigonometry. When you learn some more coordinate geometry, again come back and try this problem with coordinate geometry. And hopefully we will also study complex numbers soon, and how to apply complex numbers in geometry. Again, come back to this question and try it with complex numbers. So you can keep revisiting this problem after every 2 months, and you will find one new proof of this property. That is how, you know, nice this problem is. But for now, let us try to approach it with the tools that we know. So what we know is basic geometry, power of a point, and we want to use that. Okay. So this is what we want to do. So again, let me draw the diagram. And let me draw the circle now, because now that I have understood that the power of the point with respect to that circle is important. So therefore, that circle will be of use to us. So the setup is triangle ABC is given. I've taken any point inside the triangle. Right now, I'm taking the point inside the triangle, but as such, there is no requirement. Even if the point was outside the triangle or outside the circle, very similar proof can be followed. So it is not necessary. And actually, in my diagram, the point P is looking very much like the in circle. Let me just make it a little bit more general problem. Let me take point P here. Okay. And so now we want to prove that area of DEF is equal to 1/4 of the this is what we want to prove. So let me give you some time to think before we start with any solution. Let everybody explore their own ideas that how we can approach this problem. So actually this problem, of course, as you can imagine that every year we do discuss a problem like this. And every time I look at the diagram, some new idea comes to mind that we can try this, we can try that. So, but not of every idea doesn't always work out, but there are so many possibilities in this diagram. So let me just outline one proof which I know, and I'll leave it for you to try and find other approaches which can also work. So I am interested in finding the area of this triangle. So from all the various formulae that you know for area of a triangle, which one can be used here? So at first glance, because the problem is very nicely symmetric, right? There is no special preference given to A, B, or C. Everything is nicely arranged that it's symmetric. So if you use a formula such as half base into height, where then you're giving special preference to one side as the base and other as the height. So you're sort of introducing some asymmetry in the problem definition, which can feel a little bit less elegant, and so sometimes we hesitate to do that, but that is sometimes necessary, and we have to hope that at the end the symmetry will come back. So this is kind of a slightly leap of faith that you have to take, that let us start with some asymmetric expression and hope that things work out in the end. So the one proof which I know is somewhat like that, and so the formula which I'm going to use is that, so we know the area of triangle DEF is equal to half. So do you know this formula? The half of the product of the two sides into the sine of the angle in between. Okay. So I don't know if everybody has studied basic trigonometry and you're aware of this sine, the definition of sine cos theta. If not, I have to think how to handle that. Either I'll have one dedicated lecture to go over the basics of trigonometry, or you can try to read it from somewhere. So I'm only asking for basic things which are taught in school. So like 9th standard, 10th standard, this definition of sine theta, cos theta, those kinds of things. And so I would say this is the first level of trigonometry that you need to know. This is the definition of sine, cos, tan. I don't even require the sec, cosec, and cot. So just sine, cos, tan, then sine rule and cosine rule. So anybody who does not know anything about trigonometry, make sure you know at least these things. Okay, this is like the bare minimum you need to know for Olympiad stuff. Okay, so just these basic things, make sure you know sine, cos, tan, sine rule, and cosine rule. Then apart from that, if you go to 11th standard curriculum, there are so many other things like half angle formulae, double angle formulae, angle addition formulae, like sine of A plus B, cos of A plus B. Those things I don't expect all of us to know, and they are not always required also. But these are the bare minimum things that you need to know about trigonometry. And understand that actually trigonometry is just a notation simplifier, if I put it that way. That what trigonometry says is that if you have, I mean, something very simple. I'm not teaching trigonometry here, but just to indicate that don't think of trigonometry as some strange object which is we don't know. Suppose this angle is theta, okay, and suppose some triangle ABC, and suppose there is another triangle XBZ. Okay, then we know by basic rules of similarity that these triangles are similar, and therefore, if I write the rule, the ratio XZ upon XB, I know that XZ upon XB equal to AC upon AB, and it will be also equal to any third triangle I draw, maybe AY upon AR. So that whole etc. etc. So you see there is an infinite family of triangles which are all similar to each other. And if you choose any one of those family, this ratio is going to be constant. And so the motivation of trigonometry is that instead of talking about any one particular triangle, I'm just going to give a name to this ratio and I'm going to call it sine theta. So sine theta is the ratio of what is say opposite side upon hypotenuse. So you see, wherever you see expression like even here, what I'm writing as sine of angle FTE, you can think of that as I'm just saying that any in this diagram also, if I really wanted to be very biased, that I don't want to use trigonometry in my proof, I can draw a triangle in my diagram somewhere. Like for example, I could draw this triangle, and I'll give some special name to this point G. And instead of writing sine of angle FD, I can talk about the ratio FG upon FD, for example. So if I wanted, I could replace this by this FG upon FD, but that will just make things clumsy. So to avoid that clumsiness, trigonometry gives us a simple notation. So that's all. Just think of trigonometry as notation to simplify your life. Okay. So if you take that approach, you will start to appreciate trigonometry much better, that you will not be scared of using trigonometry. In fact, you'll see that trigonometry is a very good friend of yours to save your effort. So instead of writing, everybody sees, if I write this FG upon FD, then this FD and FD will cancel. And what we get is the standard half base into height formula. But instead of writing it that way, just this sign is helping us to simplify the calculations. And it is highlighting the fact that this angle theta in this diagram, or in this diagram, this angle FD. So any angle, any triangle, right angle triangle, which has the same angle will have the same ratio. So that is the only fact that is being highlighted over here. Okay. So just keep this in mind, that sine, cosine, tan, these are in fact some of your best friends. Sometimes some students or maybe even some teachers get the slight bias that I only want to do geometry using pure geometry. So, somehow introducing sine cos tan is a sign of, using some calculation, which is not a very elegant or very pure way of doing geometry. But that kind of bad dichotomy, I think, is misleading, and it prevents you from exploring some good ideas. So don't prefer not to fall into that trap, that thinking that if you're using trigonometry, then you are not doing pure geometry. There is no such thing as pure geometry in that sense. Okay, so therefore, this angle df into d into sine of this angle. And as I said already, that we are introducing some asymmetry, because now if you see now, this formula is not symmetric with respect to the sides df, fe, and ed, right? This is some bias is there, that we are giving special preference to df and de and less importance to the other sides. But that is fine. We will see that that is not such a big problem. And now, so the next step in our proof is we want to take each of these pieces of information, df, de, and sine of that angle, and see if we can rewrite that in some way and make it easier to process. So how do we do that? And let me get rid of this. Yeah. Okay. So how can we manipulate these three information and somehow make it more manageable? And remember, finally, where we want to go towards the power of the point. And we know various ways of expressing the power, like d square minus r square. But for example, we also know that if I just draw a chord through the point P, then that product PA into PB or whatever, that is also the power of the point P. So I can draw some suitable chord through the point P. And again, you see here, it is like, in terms of symmetry, which chord should I consider? It's almost like we are spoiled for choice. We could draw segment AP, BP, or CP and extend it to the circumcircle, and we will get that product, right? But because we have three choices, and if you choose any one of them, we are breaking the symmetry. And so we may be hesitant to use any one of them. But that is not the right idea. We have to use one of them, otherwise we will not make progress. So for example, let me just consider, which one should I consider? Okay, so I'm just extending this segment to Py. So I know that the power of P with respect to the circle is Bp into Py, or rather I should say minus of that. Okay. So I'm going very slow in this part because I want to give as much time as possible for you to think and take the next step. So on the LHS, I have DF, DE, and on the RHS, this P gamma will be replaced by BP into PY and some extra terms also. So somehow I want to relate these segments, DF, DE with BP and PY. So can you see any connection? For example, what can you say about DF and BP? Is there anything special about DF and BP? Are they related to each other in any way? Can you say anything about the 4 points B, F, P, D?
The Ptolemy's theorem.
Yeah, certainly. Ptolemy's theorem is one possibility. But the thing is, Ptolemy's theorem requires us to introduce so many other segments also, right? It is like to find the connection between two segments, you have to introduce 6 other segments. So, but that's a interesting idea, in fact. So that's what I'm saying about this problem, right? Every suggestion is a valid suggestion that could lead to some possible solution. So I will not rule out any suggestion that this will not work out. But at least the idea which I have in mind is slightly different. So what can you say about this? Yeah, by the way, why do you think of Ptolemy's theorem? Because these 4 points are cyclic, right? Because of the 90 degrees which are given, the feet of the altitude. So these are cyclic. And not only as a cyclic, so what is that circle? What is the diameter of that circle? Do you see BP is the diameter? Of that circle. So BP is a diameter and DF is some chord in that circle. Okay. Then looking at this angle, sine FDE, right? So angle FDE rather. So let us look at this angle FDE more closely. And because we in the diagram we have so many cyclic quadrilaterals, can we think of chasing angle FDE? And can we show angle FDE? Can we construct angle FDE anywhere else in our diagram?
Yes, angle PCY.
Yes, angle PCY, correct. So how do we do that? We start with angle FDE. We can break it into 2 pieces, right? So I can say angle FDE, angle FDP plus angle PDE. And then individually I can manipulate these 2 parts. So angle FDP will be equal to angle FPP. And PDE, again, the fact that PECD are cyclic. So just as BFPD are cyclic, we can also see that PECD is also cyclic. And so using that, angle PDE will be equal to angle PCE. Okay. So if I just make the markings, so I'm saying this angle is equal to this angle, and this angle is equal to this angle. And then this angle FBP, which is also equal to angle ABY, and which will be equal to angle ACY eventually. Okay, so therefore adding the 2 parts back together, right? So this blue angle which I've marked over here. So this will also be equal to this angle. And so therefore we get angle PCY. So angle FDE is equal to angle PCY. So actually, they have three separate pieces of information, and now we'll try to put all of them together. So firstly, do we understand that for DF, right? So DF is a chord in circle BDPF, whose diameter is PB or BP. So this is the first thing we understand about DF. Similarly, what is D? D is also a chord in which circle?
DPEC.
Correct, DPEC. And what is its diameter?
PC.
PC, right? So this is the second thing. And the third angle FDE, we have found to be equal to angle PCY. Okay. So let me just highlight those three pieces of information with a different color. That which segments have we found out so far? So BP. So segment BP is there in our consideration. Segment PC is in our consideration, and this angle PCY. But we have to still have to figure out how to put these pieces together. But one thing, do you notice that this angle PCY, right, which we are writing, what is the line segment opposite to PCY in triangle PCY? Do you see that segment PY is opposite to angle PCY? And why do we care about segment PY?
So we can express as the power of P.
Correct, because finally we want to go to the power of the point, right? So we already know that the power of P is BP into PY. And so that segment PY, if it enters our consideration, that will be very useful. So at this point, this problem is like a jigsaw puzzle, that I have given you all the pieces, but I have not told how to fit them together. So in fact, we will not have time to finish this today. That is fine. I don't want to rush the solution. Okay, but actually, as it turns out, to proceed with this, right, you need one more important property which is called sign rule. And as I said, that this is something that you should study independently on your own anyway, but because otherwise you might get stuck. So let me just talk about sign rule very briefly, and then we'll come back to this problem. So sign rule is a very elegant idea, and again, you can think of it as a notation simplifier in many respects, but it has more implications also. So the simplest way to express sign rule is that suppose you have a circle and you take any chord over here. Okay. So let us say the radius of my circle is capital R, and you have taken some chord over here. I am interested to know what is the relation of the length of this chord with any angle found over here. So suppose I draw any such triangle, okay, and let us give some names to this triangle A, B, C. Okay. So I am interested in what is the length of segment BC. Can I express this length of segment BC in any way? So suppose I do this. Let me consider this line. Oh, sorry, not this line. So I have considered the foot of the altitude from C to the opposite side, CF. And also look at this triangle. So through whatever properties, what angles do you know? Can you see? So if I call this as angle A, which is the convention, do you see the same angle A is occurring somewhere else also in the diagram?
Yes, sir. So angle B center and C is 2A.
Yeah. So this angle is also angle A, correct? BOT or TOB. And so what can we say about length BT now? So one way to write is that triangle AFC is similar to triangle OTB, right? By AA test, because one angle is 90° and other angle is capital D. And so I can write the ratios of the corresponding angles. But what I'm saying is that, as I said earlier, if I have any triangle, there is nothing special about triangle AFC. If I have any triangle of this kind where one angle is 90° and other angle is angle A, right? Okay. And if I just label this XYZ arbitrarily, do you see that in fact this is also similar to this triangle XYZ by the same logic? And so this special ratio YZ upon XZ, right? This YZ upon XZ ratio will not change even if I choose a different triangle. So if I choose any triangle of this family, this YZ upon XZ ratio is going to be the same. And that is why it is customarily denoted by sin A. So sin A refers to that opposite side upon the hypotenuse. Okay. And so do you see that this ratio is going to come in our diagram here, which ratio will be equal to this sin A in triangle OTB, particularly in triangle OTB, the angle opposite, the side opposite angle A, so which is side BT, right? So BT upon the hypotenuse, which is OB, which will be equal to the sine of A. That is just the definition of sine, basically. And so therefore, can we write what is the length of BC?
Two.
Yes. So BC will be 2 times BT, and which is equal to OB times sine A. And OB is nothing but the radius of a circle, which I'm denoting by capital R. So what I get is BC is 2 times R times sine A. And that is effectively sine rule. What you may know as sine rule is slightly different rewording of that. I'll come to that soon. But basically, if you want to remember sine rule, just remember this. Sine rule gives you a way to compute the length of the chord in a circle if you know the angle inscribed, right? So if I just draw that part again, if I have any chord and any angle A which is given, and if I know the radius of my circle, then the length of this segment BC is simply 2 times R, that is the diameter of the circle, times sine A. That is the sine rule.
Sir, I got a solution of that area, parallel triangle area.
You got it?
By sine rule.
Okay.
Yes, sir.
Because we are almost at the end of the time, can you do one thing? Can you write your solution and send it to me on WhatsApp, or that I'll
Okay,
take a
sir.
look and
Okay.
let you know.
Yes, sir.
Okay. But this is the hint I want to give everybody else also, because we are almost at the end of the time, that if you have a circle where I know the radius or the diameter, then I can express the length of any chord using that and the sine of that angle. Okay. So if you understood this and go back to the original diagram, so here, do you see that this setup is there in multiple places? That, for example, compare DF. So, DF is a chord, what we said over here. DF is a chord in a circle whose diameter we know, BP. So, can I relate the length of DF with BP now? So, DF will be equal to BP, which is the diameter of this circle, right? Times sine of the angle opposite DF. So, angle opposite DF means this angle ABC, the angle of my original triangle. Okay, and so on and so forth. So again, I will leave this for you to think about. So I mean, if you have never heard of sine rule before, this may be a big jump. Suddenly, learning about sine rule and applying it immediately in one problem. But we'll try to do it more gradually, maybe. So if you want, I'll have a dedicated session on trigonometry, at least the basics of trigonometry, so that everybody is familiar with these ideas and apply it. But understand, again, I want to repeat that trigonometry is not something difficult. It is just a convenience notation to express this idea that there is an infinite family of similar triangles, and we can pick any one representative of that family. That is what the sine, cos, and tan allow us to do. Okay. Okay. So again, I'll encourage you to think of this problem further. And as you may have seen, actually, I have a whole problem set. So last time we did first 5 problems. So questions 1 to 5 we solved, but there are questions 6 to 10 also, which you can attempt in the same way. Actually, I had not shared problem 6 to 10 because I was going to discuss them after doing coaxial circles part. But there is no restriction. You can attempt them now also. And you'll see that, in fact, some of them are quite difficult problems. So this is the 2013 shortlisted problem from IMO, and this is another problem from IMO. So some of them can appear to be quite difficult problems. But again, what I want to show you is that then if you apply the small steps one at a time, you can solve harder problems like that also. Okay, so I think we are all out of time. This time I'll definitely try to upload the coaxial circles lecture in next few days. Yeah. Okay, thank you. That's all.
Sir, I think I haven't uploaded the recording of the last lecture as well.
Oh, I have not uploaded? Oh, I'll do that. Sorry. Thanks for reminding.
Okay, sir.
Yeah, okay. Okay, thank you. Bye.
Bye, sir. Thank you, sir.